So, we have been looking at game playing algorithms, and in particular we are looking at board games like chess. We saw that every game has a minimax value, which is like a Nash equilibrium, but for most games that we are interested in like chess, that value cannot be computed because the tree is too big essentially. So, we adopted the strategy of doing a finite look ahead, and then we started with this algorithm called Minimax, which did a search of k-ply, backed up the values at the leaf node which were given by the evaluation function, and made its move. And then the opponent made a move, and the program again does a k-ply search. So, a sequence of k-ply searches. After that, we moved on to a pruning algorithm called alpha beta pruning, which is also like Minimax in the sense that it searches the tree in a depth first fashion from left to right, but on the way it does pruning essentially. And we saw an example where it was clear that the amount of pruning that happens depends on the order in which the nodes are generated. If the best nodes are generated first, then there is more pruning, and if otherwise there could be less pruning. So, it really depended on the order of this thing. Now, we want to look at a best first version of this algorithm, which does not do this tree scan from left to right, but has a sense of direction. So, let us begin with a little bit of a recap as to what is happening in a game. So, this is typically, this is a very small game tree that we took as an example, and a game tree is a tree which is a layered tree. At the top level, max chooses what move is to be made. So, you can see max has 3 choices, and our programs will be written from the max perspective, and our evaluation is also written from the max perspective. So, max will choose one of those 3 moves, then depending on which move max makes, min has the choice of choosing at the next level. So, max chooses at one level, min chooses at the next level, and then max chooses at the next level, and so on and so forth, till they reach a leaf node essentially. So, as you can see, there are many leaf nodes. Every path from the root to a leaf node is a game that is played, and the value of the leaf node is the outcome which says whether anybody has won. So, +1 here stands for a win for max, and -1 stands for a win for min, and 0 means it is a draw. And in the layer tree, at every layer, max tries to choose that path which will take it to a maximum value, but min does the opposite, which is to try to take it to a path which will have the minimum value. So, eventually what we get is the minimax value of the game. So, max aims to drive the game to the maximum value and chooses a child with the maximum value at every stage. Min chooses the minimum value child essentially. So, that is what they do, and as a result we get the value of the game which is called the minimax value, and that is the outcome of the game if both the players are perfectly. And we had seen that this minimax value can be computed by in a bottom up fashion by backing up values according to the minimax backup rule, in which at a min level, for example, this is a min level. At the min level, you will back up the smallest value from its children. So, min will back up 0 here, min will back up -1 here, and so on and so forth. So, 0 would come there, -1 would come there, then max would back up the maximum value. So, this is the max level, and as we will see, max will back up the value from here, because that is a value that it will get, which is 0, and from the other side it is getting -1 essentially. So, in this manner we can back up the values from leaf nodes and determine the outcome of the game, which is the minimax value, and we had seen this earlier. So, you can see that at the min level we are backing up the smallest value, then at the next max level we are backing up the largest value, and so on and so forth, till the values propagate all the way to the root essentially. Now, this is the case for a tree which you can traverse completely, but we had seen that game trees for games like chess are too huge to be done, and that is why we had this notion of the evaluation function and so on. But the basic idea was the same, that the minimax value is the best that can happen as seen on the horizon, essentially as seen by the evaluation function on the horizon. Now, for this best first approach that we want to look at, we do a recap of what do we mean by a strategy. A strategy for a player is a subtree of the game tree that completely specifies the choices for that player, essentially. And we are interested in max, so we will be generally interested in strategies for max, and this is how you construct a strategy. Traverse the tree starting at the root. If the level is max, choose one branch below it, because we are freezing the choices for max. But if the level is min, then you must choose all branches. That is because we do not know what max is going to play, min is going to play. So, max's strategy must take into account all possible min moves, essentially. Later on, when we look at this notion of goal trees and or trees, we can see that at the max level you have to choose only one, but at the min level you have to choose all, essentially. So, the solution for us is going to be an optimal strategy, which later on we will see when we look at goal trees that corresponds to AND. So, we will see that the max level corresponds to OR and the mix level min level corresponds to AND. So, at the max level you choose any of the branches, so it is an OR level in that sense. At the min level you have to choose all the branches, so it is an AND in that sense, and we will look at this formulation called AND OR trees a little bit later in this course. So, this is a algorithm for constructing a strategy, and then we looked at two strategies here. One is in red, one is in green. So, these are strategies for max. So, as you can see at the top level there is only one edge we have selected for max. So, in the red strategy it is a middle edge, and then at the next level we have selected all, because we do not know what min will play, and then so on and so forth. So, we traverse this entire tree constructing these two strategies. One is, let us call it the red strategy, and the other let us call it the green strategy. So, this is based on the color of the edges. Now, you can see that once max has frozen its choices, it is up to min to decide where the game will go, essentially. The value of the strategy that max chooses is decided by min, because max's choices are frozen, and it is only min who can choose now. And who, being also rational, will choose the minimum value from a leaf. So, if you look at the red strategy on the right, you can see that all its leaves are labeled with W, essentially. So, remember W is the same as plus 1, essentially, and draw is 0, and L we do not have L in any of these max's strategies, but if L was there somewhere, then that would be equal to minus 1. That is why this max is maximizing the value, trying to maximize the value, and min is trying to minimize the value. So, if you look at the strategy on the right, all the leaves are labeled with W or a win for max. So, min really can't do anything, and it turns out that that strategy for max is a winning strategy, essentially. If max can find this strategy, then max will win the game. And we had seen when we had computed the minimax value of this game, that its value was actually plus 1, because now we can see that max can always choose this red strategy and min can do nothing about it, essentially. But if max were to make a mistake, just to illustrate the point, then and choose the green strategy, then min will drive the game to a draw, essentially, because once max makes this move, min can simply make this move, and the game will end there, and it will be a draw, essentially. So, the value of a strategy is the minimum of the value of the leaves in the strategy, because that is where min will drive the game to, essentially. Now, we are writing these programs for max to play whatever game we are talking about. We need to find a strategy for max. So, our task is to find the best strategy for max, which is equivalent to saying find the best move for max at the level of the root, because we have seen that the way we play this game is we do k-ply search, make a move, then wait for opponent's move, then again do another k-ply search. So, essentially finding the best strategy amounts to saying that this is the move that max will make at that level essentially. Now, how many strategies exist for max? So, let us look at this tiny game tree. It is a binary game tree. At every level there are 2 choices, and it is 4-ply deep, as you can see. There are 16 nodes at the leaf level. Now, at the top level max has 2 choices. So, max can make either the left move or the right move. Then at the third level, max has 2 choices for every node essentially, which means that if you look at a combination, then if max chooses the left path or chooses a strategy which is going down this left branch, then this strategy can be refined into 4 different strategies. So, in one strategy you will choose, let me write it here, left and left, which means that you are choosing this left here and this left here. So, this is just a notation that we will use for determining how many strategies exist. So, max after choosing the top move at the top, which is L, it can choose LL at the next level. It can also choose LR at the next level, which would mean that it chooses the left branch for its left subchild and the right branch for the right subchild. So, let me use it, let me label it like this. If this is L and this is R. So, LR means the left choice on the left subchild. There are two children for min, remember, and for each of them max has to decide as to what is the move that max will make if min were to choose any of those 2 moves. So, we have seen 2 L, 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 R. There can also be R, L and R, R. So, there is a 4 combinations of the strategy. So, this strategy corresponds to actually 4 strategies. This move corresponds to 4 strategies, which are, we have used this notation of LL, LR and so on and so forth, and the same is on the right hand side. So, you can see that max has 8 strategies essentially. So, as a small exercise, I will ask you to take that for any arbitrary game tree with branching factor B and depth D, how many strategies does max have? The task is to choose between these strategies essentially, but we want to do it in an efficient fashion. Now, we have a notion of a cluster of strategies. If you take any node at the leaf level, any node on the horizon, remember that this level is the horizon. What do we mean by the horizon? That it is a terminal node beyond which we do not search, but instead we apply the evaluation function, and the numbers written in these squares at the bottom are the evaluation functions. Now, if you take any node, for example, this node 15 which I have colored here, that represents more than one strategy. In fact, it represents a cluster of 2 strategies. Which are the 2 strategies? One strategy is so remember that we had called this as a left choice. One strategy is as shown in gray, which means, which we can call as RL in our notation, which means for this choice we choose R and this choice we choose the left this thing. If that is the case, then the leaf nodes in that strategy, there are 4 leaf nodes in that each of the in that strategy, are the ones which are shown in gray here essentially, 15, 11, 12 and 8 essentially. So, if max chooses this strategy L, RL, let us call it. So, this is RL is below and L is at the top. If max chooses the L, RL strategy, then the 4 leaves are 15, 11, 12, 8 and min will drive the game towards 8, as you know, because it is min who decides what happens after max has chosen the strategy. But what we are trying to point out here is that this node 15 is also a part of another strategy. What is the other strategy? 15 of course is part of R, as you can see here, but on the other choice if we choose R, then we get these 4 nodes. So, these 2 nodes are common to both the strategies. What are the 2 strategies? This is L, and then it gets modified into L R L and L R R. I hope this notion is not confusing. We are just trying to identify these 2 strategies. So, this is the leaves in L R L, these are the leaves in L R R, and but they are different leaves. As you can see, the R strategy, which is shown in red, has 9 and 13 instead of 12 and 8 essentially. So, this is not there, this is not there, and but these 2 are there essentially in the second strategy. Now, if you think about this notion that the value of a strategy is the minimum of the value of its leaf nodes, that means if you choose any leaf node, we have chosen only one at this moment, which is 15. So, we know that this 15 is going to be a upper bound on value of both these strategies, which we have called LRL and LRR essentially. Why is that? Because it can only go lower, because we do not know what the other leaves are, we have not yet explored it, and that is how we are going to do this search. But we know that this 15 is going to be an upper bound. They have this upper bound, both these have this upper bound of 15. Why? Because we have seen 15, and we know that if there were any lower nodes, min will drive it to that, otherwise 15 would be the value of the strategy. So, value of the strategy, these 2 strategies LRL and LRR cannot go below 15. So, every leaf node is going to be an upper bound on the values of the strategies which are there in a cluster, and every leaf node represents a cluster of partial strategies. And as we have seen here, this leaf node 15 represents 2 strategies, LRL and LRR essentially. So, 15 comes from L and R, and the other 2 strategies vary on the third this thing, whether it is L or R. So, by looking at a leaf node, we get some idea of what is the value, or at least what is the upper bound on the value of the strategy. So, this is very similar to what we did when we were looking at branch and bound with the travelling salesman problem, that we took a partial tour and then we looked at values which were lower bounds in that case, because there we were trying to minimize the cost essentially. In the same manner, we are looking at partial strategies or partial solutions here and estimating upper bounds on how big that value of the strategy can be. And by looking at this, we can see that if we just look at the node 15, it is part of 2 strategies which we have called as LRL and LRR, and both those strategies cannot become bigger than 15. So, we work with this idea, and we come to this algorithm called SSS star, which is the best first version of the game searching and the algorithm for searching the game tree. It was devised much later in 1979, as you can see, and it being a best first approach, it follows our general best first principle, which says that refine the best looking partial solution till the best solution is fully refined. In this case, a solution is a strategy and a partial solution is a partial strategy, and we have seen that in the previous slide we saw that there was a partial strategy which was identified by one leaf node called 15 essentially. So, what do we need to do now? We want to find the best strategy for max in general. So, we must create a search space in which all strategies are taken care of. That is what we said when we were looking at branch and bound also essentially. So, algorithm SSS star searches in the solution space. First defines clusters to cover all strategies. So, we want to cover all possible strategies because we want to choose the best one, and all cluster, each clusters will be defined by one node to start with. Just like we saw 15 in the recent case, it covered two, it was a cluster of two strategies. So, we want to cover all clusters and each cluster would be represented by one node, and that would be an upper bound on the value of all the strategies in that cluster. So, this all is important because of completeness. We do not want to miss out on the best strategy. So, the procedure for constructing the initial clusters, which is what SSS starts with, is as follows. You start at the root node and you repeat the following. At the max level, choose all children, and at the min level, choose one child essentially. And in our illustrations, without any loss of generality, we will always choose the leftmost child. That is what we have been doing. For example, even in depth first search and such things essentially, until the horizon is reached. Now, you can see that this is the opposite of the definition of a strategy. We are also constructing a subtree, but in our subtree we are choosing all children at max level, and we are choosing one child at the min level. Whereas, a strategy, if you remember, is a subtree in which you choose one child at the max level and all children for the min level. So, there should not be any confusion between these two things. So, what we are looking for here is a set of clusters which will cover all strategies, and because we want to cover all strategies, at every max level you must choose all nodes essentially, and at the min level we choose only one, because we just want a estimate, we want an upper bound on the value of the strategy. So, this is the process of starting the search, which is to find all the clusters in the game tree essentially. So, in the small game example that we saw, you can see that there are 4 clusters. We have already seen this node 15. We saw that 15 was part of 2 strategies, or 15 represented a cluster of 2 strategies, or 2 partial solutions, or 2 partial strategies. Likewise, 21, 5 and 13 also represent clusters. How do we arrive at these particular leaves? By the strategy that at max level you choose the subtree with all branches, and at the min level you choose only one essentially. And so, if you follow this process, you can see that we end up with these 4 leaves essentially. Remember that we had observed that this particular game tree has 8 strategies, and then we saw that one cluster which was represented by 15 covered 2 strategies. So, you can see that these 4 leaves will cover all the 8 strategies. Each leaf will account for 2 strategies.